And everybody can hear me?
Yeah.
Perfect.
So you can just drop that in your pocket.
Does it matter if it's upside down or not?
No, just anywhere.
Okay. All right, put it right here. Good?
Yeah.
Excellent. So I'm tempted to start maybe a minute earlier just because to squeeze in as much as possible so I can go a little bit less fast. It's never slow. How's it been so far? Good, excellent. This is my 8th year, I think, at Code Camp. And I always come back because I've found, you know, it always varies depending on where you go, but I've always found that the audience in Silicon Valley Code Camp is always very appreciative. And why more so here than else? I don't know, but, you know, it does make a difference. So, for me, maybe for others it's different. I don't know. Well, I'm from around the area. I've been here for a long time. I'm a pseudo-Californian. And I can't believe how long I've been here. Where did the time go? Now I know why people say that. Before the recording starts, well, I was going to tell some lame jokes, but I'll be correct, not and err on the side of caution. So, let's see. I think it's 43. Shall we start? All right. Welcome, everybody. I'm glad you could make it. I'm glad to be back, and I will be your tour guide for the next 50 minutes for deep learning concepts, then some TensorFlow stuff, and then TensorFlow.js, which is the TensorFlow toolkit in the browser for doing deep learning sort of stuff, neural networks. And so I'll put the slides online because I'm going to skip some of them. And then that way you can go back if you want to look at them, the ones I skipped and the ones that I'm doing to kind of bring it all together. I'll show you about something like this artificial neural network, how that works. Then we'll look at a linear regression, which is not deep learning. It's 200 years old, the core of a lot of probability statistics. And it's essentially useful to know. It's kind of a must-have if you're going to be involved in data science. You can't be in data science and not know linear regression. And it sort of helps to understand some of the other concepts. And also then a convolutional neural network, which is used for image classification. And so, I don't know, I think it's on. So Yash, do you know if it's recording? Yep, it's on. Okay. All right, so I'm used to stand here, but that's okay. Here are some of the things we'll look at. And you notice they're clustered by colors because they're things that are related. And they're called hyperparameters, and they're things that you specify, that you set before you do training for a neural network. And we'll go through some of them and see, you get a kind of an idea of when they're used and why they're used. And as you can see at the bottom, we're going to get to the TensorFlow stuff there. So just to start at a high level, this is the diagram I like to include. It's a little bit out of date because you don't have to learn all of this, by the way, to do deep learning. We're going to concentrate on the red dot, parts of it. So with data science, it kind of does overlap with deep learning because you can use Keras and TensorFlow with R in RStudio. And there's something that's not there. It's called reinforcement learning. Think AlphaGo, or those systems that'll play a game a million times and that sort of stuff. But it's also with robotics. And it's not actually deep learning. It's part of machine learning, but there's something called deep reinforcement learning, which is the kind of the intersection of the two, or the union, something like that. And it's actually going to be probably a very big area in the next few years. It could be the driving force behind deep learning, which kind of sort of drives machine learning, maybe sort of. And so the diagram on the right, the three circles in simplified terms, AI is sort of, if you think of the classical, maybe old school kind of stuff, it was in the 50s it started coalescing together. I mean, things have been happening before then. But it started with sort of the official formal start was 1956, 62 years ago, a conference at Dartmouth where the term AI was coined by John McCarthy, who invented Lisp. And so the difference in simplified terms, AI, traditional, focuses on rules, plus some logic, and of course some data. And it can become very complex because you have to specify the rules for a system, what something is or is not. It could be hundreds of rules. And yet, it still led to the development of expert systems in the 80s, which are very, very powerful, still in use today, actually. On the other hand, machine learning and deep learning, the focus is on data. Lots of data, lots of inexpensive compute power, algorithms, new ones, modified, improved ones, and in the case of deep learning, also neural networks, which we'll see in a minute. And so the really kind of interesting thing is, first, the stuff for deep learning, the stuff I showed you on that list, a lot of that stuff was developed in the 80s. It's just that we didn't hear about it. It wasn't the focus. The kind of perfect storm, if you will, for deep learning happened during this decade. In fact, probably from 2012 onward. And so it's very recent, as you've noticed, the influence of deep learning, and it's going to continue. So just a few use cases. You know, I can summarize it saying pretty much everything you can do with deep learning. And here's the neural network I was telling you about. So if you look at this, it's kind of confusing when you first see it maybe, but the idea is that, this is with the hand-waving part, and I'll get more specific in a minute. So you start with the data, numeric data for the input, and you process it, transform it, whatever that means, as you go from left to right. And then at the end, there's the framework that you use, for example, TensorFlow or Keras, whatever one you're using. It does some of the heavy lifting to calculate numbers in order to adjust the weights of those edges going in the other direction. So from left to right is forward propagation, the other direction is backward error propagation, or just back prop. Of course, nothing's populated yet, but just bear with me for a minute. So as you go back, you update those numbers, and then you take another input of data, another row of data, maybe from a CSV, from a spreadsheet, and repeat that process. So you go through the whole data set, however many rows there are, and when you finish that, that's called an epoch, E-P-O-C-H. And you might do 20 epochs, or however many you want. Again, the choice is yours. So with this forward and back and forward and back, that's the learning, updating those edges. The learning, the process for the neural network, training the neural network, training the model, it's all the same thing. Okay, so notice that on the right side, there's an output layer. So that's going to be whatever it is you're trying to classify. So bird, dog, cat, fish, for example. If you want to look at Boolean situations where is the temperature going to go up or down, the stock is going to go up or down, spam or not spam, it would be two outputs. If you ask the question, what will the stock price be tomorrow, that's different. That's not Boolean anymore. It's going to look something like this. Don't worry about the number of connections here. The point is that there's one output. So what happens is, like in a housing situation, you have rows of data with attributes, values, square feet, age, number of bedrooms, et cetera, and then there's a price of the house that's fixed. So what happens is you feed in that data, everything except that price, and it comes out and it computes something, and it's going to be different because you're populating the values arbitrarily. And so you compare the difference, that's the cost, hence the cost function that I mentioned before. And there's also this thing about descent. You want to minimize the cost, so what's the steepest way to go down a hill? Or the fastest way, rather? You go down whatever the steepest is, the gradient, the derivative. And there's something called the learning rate, which is a number between 0 and 1, controlling the rate at which you kind of move forward. So those three go together. I'm kind of jumping around a little bit, but it'll all come together. And so in this case, when is it a classifier versus regression? Whenever the set of outputs, the classes, can reasonably fit in a drop-down list, whatever that means. So MNIST is for the digits 0 to 9, so there would be 10. The states in the US, it would be 50. It would be one of those probably. If it's the price of a stock, well, that's considered continuous, even though the price of the stock is the granularity of whatever monetary unit you have, plus or minus, right? In between, there's a lot of numbers. So it's not mathematically continuous, but in deep learning, it's close enough. And you'll find a lot of things that are like that in deep learning and machine learning. Close enough, good enough, depending on what your success criteria are. That's the key. So there's a lot of control you have in your hands, but there's other things that you don't control, which is what makes it interesting in terms of defining a neural network and then training it. So let's go back to the hidden stuff. These are intermediate computational layers. How many layers? Hyperparameter. How many neurons in each layer? Hyperparameter. How do you initialize the edges? Hyperparameter. There are several ways to do it. One is to use random probability values from, say, normal distribution, n0, 1. So let's just assume that that's done. So then when we have that input vector of numbers, in order to get to the second layer, the representation between them is a matrix. So now you have a vector and a matrix. You multiply it, you get another vector, and you continue all the way to the end. And then you have this, as I mentioned, cost function, the descent thing that's called an optimizer. There are several types that you can choose from. Another hyperparameter, and then the learning rate. And so it does this calculation stuff. So there's the derivative, partial derivative, chain rule, all that stuff. Did anybody take calculus? Okay, so either you will really like it or the nightmare returns. It's how it is in life, it seems, you know. And so then the back calculation. So if in the case of MNIST, you have 55,000 images that you can use for the training. And you do it typically common. It's not unusual to do it 20 times. What does that mean? 1.1 million times going forward and back, forward and back, updating those weights. And then at the end, you calculate whatever you got that was correct, the accuracy. I'm skipping over that part. And you might get a number like 90%. And that number by itself isn't really that significant because you don't know, it has to be in relation to something else. So then you can use another part of the data set. It's actually, there's three. There's the training part, then there's the validation part, and then there's the test. And so you do the same thing with the validation data, compare the two percentages, and if they're roughly the same, then you got a good model, and then you try to improve it. If it's significantly lower, the second percentage, then you probably have something called overfitting. Has anyone not heard of that term? Everyone knows what it is? Oh, okay. Think of it as signal and noise, and if a significant part of the noise is treated as signal, that's essentially overfitting, sort of, kind of. And there are several techniques for dealing with that. One is called the dropout rate, which is a number between 0 and 1 that's treated as a percentage. So 0.2 is 20%. And you define it as part of your neural network. You'll see it later. And what it means is whenever you do a forward pass, let's say it's 0.2, you randomly select 20% of the nodes and just ignore them. Then the next row across, another random 20%. You don't drop them, you just ignore them. The interesting thing is, it actually works. Now, for this example, 20% maybe, but if you get 30, 40, 50% might be a little bit too much. But with something like this, if you have 100 million edges, you drop 50%, you still got 50 million. And the thing about it is that it works. And it's Geoffrey Hinton, the godfather of deep learning, as they call him, came up with that. He came up with a lot of other things as well. So, yes. You ignore it. You ignore them, yeah. Yeah, you're thinning the network, kind of, the neural network, sort of. I call it the ginkgo biloba of deep learning, which, in case you don't know, it thins your blood. That's how it works. So, you feel lighter, stronger, and, it improves your memory too. And so that actually does work. That's the interesting thing. Now, what's the value? That's something that you decide because it's a hyperparameter. So far, how many hyperparameters have I described? 3 for the initialization, 3 on the other side. This one down here, drop it right, that's 7. There's an 8th one. Very important because this won't work without it. This system that I described is linear, which means that all those matrices, matrices have a property. If they're compatible, you multiply them. You multiply them all together to get one matrix, which collapses this to input, one matrix, and output. And we want to prevent that from happening, so we need nonlinearity, which is handled by something called an activation function. And that's a hyperparameter. That's the 8th one. And there are several of them. There's sigmoid, tanh, ReLU. And so what happens is you select your activation function. You get that, it started at the beginning. You got the vector, multiply by the matrix, get another vector. And then each of the numbers in that vector, you pass through your activation function to get another vector. And then repeat the process. Clear as mud? For example, convolutional neural networks, which are about 60% of the neural networks that exist as of 2 years ago. Image classification. And I'll show you one in the next slide. So the theory is actually applicable to real-life stuff, actually in many cases. Good question. You're the first person who's actually asked that. Everybody else is just thinking about it. So, I'm dazed and confused too, one of my favorite songs. And so by doing this, you prevent this multiplication of all the matrices to get one matrix. That's the key. So by analogy, if you think of, say, one of my favorites is speed bumps in a parking lot. You can't go through all the way from beginning to end. You have to slow down, then you speed up. It prevents your forward constant speed, your momentum. So kind of that idea with this, or with an obstacle course or toll booths or whatever. I know it's a little weird, and it will feel weird for a while, but then eventually when you see it 5 or 6 times, it starts to feel sort of normal, kind of. But it does work, and it is necessary for the reason that I mentioned, to prevent multiplying the matrices together. So the question of an application, why, when, how. Everybody can tell the difference between a puppy and a muffin. So you can, I'm going to show you an image here. Tell me how many of these you can detect correctly, how quickly, and for how long. I give up after about 10 seconds because, I'm looking, every time I look at it, I have to go count because I'm not really quite sure 100%. There's a couple of them, they're like, wait, maybe, yeah, kind of, sort of. So imagine a neural network that's trained to do image classification and is processing 1,000 images per minute, maybe more, maybe 10,000, and 99.5% accuracy. There's no way you can compete with that. This is a facetious, contrived example, obviously, but there are other situations where it's very important, like detect radiology, trying to detect cancer or skin cancer, or trying to detect macular degeneration. So in those cases, it's a little bit more complicated because the images, the X-rays, may not be publicly available or accessible, and they aren't necessarily clean data. So even humans looking at it, it's very difficult, obviously. You need people, radiologists, to do the processing. It's very slow, painstaking, tedious, and error-prone, even for them. But there are systems that have been trained that can actually have comparable accuracy. That's where the work, the heavy drudgery, error-prone, time-consuming stuff, that's where these things really have the value. So that's why I'm here talking about it. And so one of the things I mentioned before about the activation functions mentions sigmoid, tanh, and ReLU. They're based on something, I don't know if you remember, Euler's constant. You remember log base 10 logs? Do you remember ln base e? Yeah, that number. And it's a number like 2.71828. It's actually an irrational number. This is the graph of y equals e to the x. And what's interesting is it's the only non-zero differentiable function in the plane that equals its own derivative. It has a lot of interesting properties, shows up all over the place. And so here's sigmoid. And if you multiply top and bottom by e to the x, you get e to the x over e to the x plus 1. So the numerator is always a little bit smaller. But it's increasing monotonically to the right toward 1 and decreasing monotonically to 0 on the left. And every number between 0 and the real line can be mapped to some number between 0 and 1. Just pass it through that function. So the vector of values, you just, whatever the numbers are, plug them into that formula, that's how you get the new vector. And so what's interesting, bit of a digression, the reverse is true. If you take any number between 0 and 1, find out where it intersects, let's say 0.6, where it intersects, the horizontal line intersects that graph, you'll have a real number. So as you get up to close to like 1, like 0.99, that number is going to be way over there. And likewise, when it gets close to 0. What does that tell you? Something kind of interesting. People who, anybody study mathematics as a major? Okay, you may remember, and if you don't, I'm going to tell you, the cardinality of the interval 0, 1 is the same as the cardinality of the infinite number line. Because given one, I can map it to the other, and I just told you how. In fact, any interval, take any interval 0, epsilon. Epsilon is as small as you want. Think of the smallest number that you can think of. Take half that, it'll still be true. Just some of the fun that you missed out on when not being a math major. And so, similarly, here's tanh, a little bit different, but there are different ways to represent this activation function. The difference is it's between -1 and 1. Now, these two were the first ones. They're not commonly used anymore. It's ReLU, which is this, which is just 0 for negative. It's max of 0, x. So it's the identity when it's positive, 0 otherwise. And it's continuous, but not differentiable at 0. So sometimes they use ELU, exponential, which makes it kind of smooth. There's also leaky ReLU, where it drops down to the left instead of 0, it kind of goes negative. And then there's the one that cuts off at 6, ReLU 6. That's specific to TensorFlow. And so this is the one that's used most often now. Those other two are still used in things called LSTMs, long short-term memory, GRUs. They're these gated recurrent neural networks, and they have these gates, like forget, input, output. That's where they show up. So they're not ignored. They serve a different their value is in a different place, not in the situation we've been looking at so far. And this one is useful too because this is the exponential version of the proportional value of a set of numbers. The advantage of this is the numerator is never negative and the denominator is never 0. This is the thing that's used at the last layer. Remember we saw cat, dog, bird, fish? There's that layer just before that. Well, you connect everything from that to the output, all the edges connected, and you use this. Why? Because any set of numbers that you feed in here will result in a set of numbers between 0 and 1 whose total sum equals 1, which is a probability distribution. Because those outputs that you saw, the 4 or the 10 for MNIST, those are going to be probability values. And what you do is you look at, well, what's the biggest probability in this set? Oh, it's in position 2. Since it starts at 0, that means the number 3 if you're doing MNIST. And then you look at the thing that you put in. What's the index for that hot encoded 0, 1 vector? Oh, it's 2 as well, index. You compare the indexes. Very key point. If you compare the numbers, it will fail 100% of the time because the outputs will never be 1 and they'll never be 0. So it's 0.8. That index is where there's the 1. It's the same. So it could be 0.9, 0.8, 0.7, 0.6. Will that work? If one number is 0.6, the sum of the other numbers has to be less than, at most, 0.4. What about 0.5? Still true. Even 0.4 would work, which is not very accurate, 40%. The interesting thing about it is it actually works. That's what's amazing. So that's the purpose of one of the reasons for the softmax. And here's kind of the Python code for the sigmoid tanh ReLU, and you can look at that. It's the same as what we just did, generalized from scalar to more of a set of values. And this, we pretty much summarized it, and I'm speeding up a little bit because I want to slow down a little bit later. Now let's go back to 1805. Carl Gauss came up with the technique for linear regression. Does everyone remember the equation of a line in the plane? Gee, you're right. Which represents every line in the plane except a vertical line, which you could actually use ax plus by plus c equals 0, but we're going to ignore vertical lines. We don't care. So with this, the m is the slope, b is the y-intercept where it crosses the y-axis, and that's also the bias. So in a very idealized case, we're not going to worry about corner cases, different types of distributions. We're just going to conveniently have this set of data. So the idea is actually comparable, sort of with, you could have a quadratic, cubic, other functions if you wanted with other types of data. But let's just pretend that this is the situation we're faced with. That line there, if you take, it kind of seems to be the best fitting line somehow. Because if you change b, increase or decrease, it's like a vertical shift. It's moving away from that best fitting line. And if you take m and you change m, you're rotating it. So you can see somehow or another, this fits. Why is that? The idea is the best fitting line is the line that's least far away from the points. And what does that mean? This is where Carl Gauss, 1805, each of those points there, the black dots, those are some of the points on the preceding slide. And what we do is, what we want to minimize, this is the cost function aspect, is the sum of the squares of the differences between the y-coordinates of each point and the y-coordinate of that point if it were on the ideal line, the best fitting line. That's the thing we want to, so the sum of the squares. And so m and b are two independent variables. So if we took the floor as the plane for m and b, so there's the origins there, there's the m-axis and the b-axis, then that third thing has to be in 3D. Has to be a surface. And it's not elliptic, it's not hyperbolic. What's the other quadratic? The math people? Parabolas. Actually, it would be paraboloid, and it looks something like this. And this is called a convex surface, which means it has either one max or one min. Obviously, it's the minimum. If you go to that point where it's the minimum, the value of m and b is the value for that best fitting line. So you're done. Completely. This is in statistics. You don't need neural networks, nothing of the sort. So there's a closed form solution. You can also do this with neural networks if you want. And here's the interesting part. Using a neural network to solve this is a very heavyweight type of solution. And what you will get is an approximation. You don't get the exact value of m and b. So for instance, if we had m equals 2 and b equals 1, through a neural network you might get 2.004, and b might be 0.997. It's only an approximation. That's the thing to keep in mind. It's important because if you go to a bank and ask for a loan and you get turned down, they have to give you a reason legally. And with neural networks, it's just an approximation. You can't tell them their lambda score is less than 0.3. You have to give them a specific reason. So you can't use this for financial transactions. You can't say, I transferred $1,000 to this account more or less. You want the exact number repeatable every time. So not transactional data, financial data. So it's more about looking for patterns. That's one way to look at it. Okay, so now, I'm not used to flipping back and forth like this, but so let's take a case, very crude, simple, trying to look at number of square feet for horizontal axis and vertical axis cost of a house. Very coarse-grained. And using a line, I would not rely on something like that. But if you have more attributes, or as they call them, features, you're probably going to get something better. Now, I mentioned before, I said 10. There are data sets available. They have 34 columns. And they look at things like what's the crime rate of the nearest zip code to that house? All sorts of things. Some of them are not obviously visible, but they do have an impact potentially. And so these attributes here, the features, if you have 6 columns, and the 7th column is the cost, the price rather, those 6 are the 6 inputs. Remember that first layer? That's what if it's 10, then there's 10 inputs. If there's 30, then it's 30. The one at the end is going to be 1. It's regression. The in-between part, that's what you decide. And rather than rely on trial and error with lots of trial, lots of error, it's probably to your advantage to use a pre-trained model where somebody's done it already, the training with something similar data set. 89% of the time and effort is done. You just apply some of your data to it, and then you tweak it, and then you'll have your trained model. That's actually common. Yes? Sure. This doesn't, good point. This doesn't predict necessarily with high degree of accuracy one state in the United States or even one part of the state versus another. It's going to be dependent on the nature of the data, which raises another point. The data is very, very critical. You don't know the distribution of the data. I mean, the one we do with the line, that's the trivial case. It's never like that in real life. But the principles are there. So, for example, the idea of minimizing something, you want to do that programmatically. Imagine you had 500 columns and you had 1 billion rows. You can't graph that. Which 2 would you pick if you wanted to graph it? It's ludicrous. There are techniques, principal component analysis, to try to reduce the number of columns, figure out the ones that are most important, or linear combinations thereof, to kind of, maybe there are 5 out of the 100 that account for 99% of the effect. So there's that small diminishing long tail. That's another consideration. Again, you decide that. Or the person with domain expertise. And if you have a set of data and you want to drop a column or add a column, can you do that? When? How? If you don't have the knowledge, then you kind of need to get someone there who does. Another part is the data cleaning with all of this stuff with machine learning. 50 to 80% of the time is dealing with data. Missing rows, or duplicate rows, missing data, incorrect data. What do you do? If a data point is missing, what value do you assign it? Who knows? 0? The median? The min? The max? Do you drop the row? Can you drop the row? What if it's an outlier? Do you just drop rows that have outliers? If you find one, what would you do? Well, if it's the stock market, you probably don't want to drop the outlier because it's critically important, right? If you're trying to predict something, you got to take into account that sort of thing. So there's a lot of stuff with data analysis that's involved. Probably that's why a lot of the time spent involves that with machine learning, not so much with deep learning, which is one of the reasons why I like it. It does the work for you in many cases. Okay, so moving on, I'm going to skip this. Just to go back to the cost functions, here's the one I was telling you about. This is for mean squared error. Here's another one. At 0, it's a minimum in one direction, another direction, it's a maximum. It's called a saddle point. These are not so good, but they do exist, and you might encounter that. So how do you programmatically detect that you're there and move away from there? That's what these frameworks are meant to do for you, for us. This is cross entropy, and it comes from something called entropy, sort of, and the cross entropy is the difference, the extent to which 2 probability distributions differ. You've got the original data set, that has a probability distribution, no idea what it is. You've got your trained data model at the end, that has a probability distribution. You compare the 2. You actually take the ratio and then you take the log, always logs in this stuff practically. And then if the 2 are the same, the ratio is 1, the log is 0. So it gives you a measure of some idea. Just like with statistics, you look at the mean, the variance, standard deviation, the R squared, F score, all that stuff. They're just trying to help you get a sense of what the data is like without actually being able to graph all of it. And here's some, remember I mentioned optimizers. So SGD, stochastic gradient descent, that's the one where you update every time. And there's some other ones, and they differ. You can look online to find out the details. This is sort of the summary of what we talked about, kind of. CNNs versus RNNs, convolutional neural networks, like we saw an example before. RNNs are recurrent neural networks. Now, the interesting thing is they're a lot more complex, harder to train, much more time-consuming, but they can solve some very interesting problems. You can do a lot of things with it. What's interesting is you can do NLP, not just with RNNs, but with CNNs. Now, how would you do that? How would you do audio? How could you detect that if you need numeric values? Remember, for the housing situation? So in the case of audio, it has a frequency. In fact, if you go look, and I did, just curious a while ago, when you look at sound waves, there's about 12 different features involved, none of which I'd ever heard of. The only one was the frequency. But you can determine those values, pass them in, and then train it through a CNN. Because the CNN only is concerned with the fact that you have numbers coming in, numeric values. Where it comes from doesn't matter. Similarly, with NLP, you can take words in a sentence and map them to numbers. And then you pass them in, voila. And so there's kind of a blurring where you can do both. CNNs and RNNs can do a lot of different things. And with reinforcement learning, also NLP, and deep reinforcement learning. And they have different results and different accuracies. Yes? There are lots of data sets available. Go to Kaggle. Go to GitHub. Government. All that stuff has to be publicly available. Lots of real estate data, tons. Pharma-type data, I think, as well. Is that right? There's various types that's available. Probably, and the extent to which that data is clean or not, well, you have to kind of look at it. So there are many data sets available. And when did Facebook close its data? You said? When was that? Oh, okay. I don't use their data, so. Oh, Twitter. There's another one. Okay, so now we're going to get to the weird part. How the heck does a CNN work? Well, there are three parts, typically, generally, for the basic standard scenario. There's the convolution part, and then it generates this image map, and then you use ReLU to make sure that all the negative values are replaced with 0. And then you do max pooling. So probably the first part, the convolution, this is what was being done in the 80s, by the way, Jan LeCun over at Facebook now. The idea is that your eye has different parts that detect different shapes. And parts of your eye detect vertical segments, some will detect horizontal, other sorts of shapes. The idea is that this is the framework does this for you. You get these by default, typically, customarily, 3x3 matrix of numbers. And you say, I want 16 of these convolutions, 3x3. And you take the image, well, you don't see it here, but the image itself is a bunch of numbers, right? RGB, 0 to 255. And you perform essentially the inner product of that 3x3 and as you scan it across. And that results in this other thing I call this feature map. It's sort of like a heat map, kind of. But you got to make sure the numbers are non-negative. That's where the ReLU comes in. So, for example, I don't know if you can see this very well, but the green on the left, and then on the right, you see where it's gone through a few passes, right? It gets to that. You see the 1 is at 42. All the rest is 0, so the result is 42. And so you do that with each of these images, the features, excuse me, the convolutions. And then you do the ReLU part, and then you do this. First of all, let me give you some more examples. These are filters that you can actually use. They're used in GIMP, Photoshop, and the rest. They're real. And here's some more. There are other ways of doing edge detect. That's just one of them. And then this is max pooling. You notice how we took the maximum of each of those 4 squares, threw away 75% of the values. And you're probably skeptical, but I will say this, that it's like image compression. You have lossless and lossy. JPEG is lossy, and it still works. So the technique works. And you could use the average, the square root of the sum of the squares, blah, blah, blah. It works as well as any of them. Put a big asterisk next to this because, once again, Geoffrey Hinton came up with something called capsule networks that are better able to deal with images that can deceive neural networks. They're called GANs. They're not perfect, but they do help. And a little harder to train, a little bit more work. But there's a reason for their existence. So that's about it, I'm going to say, except for here, we've got a panda, a weird thing, and a panda. The thing on the right is a superposition position of the two on the left. And look what we have. 57% confidence that it's a panda, and a gibbon at 99.3%. Can you tell the difference? I can't. But the numbers have been modified, the values, in such a way that you can consistently defeat any neural network. And last November, someone came up with an algorithm, it's on arXiv, it's a paper, that can create this sort of effect by modifying 1 pixel in an image. And it gets worse. Somebody's doing some work with audio to sort of corrupt the audio so you don't know what's it saying, who said it. So let's review. We got fake news, we got fake images, we got fake voices. And let's not go anywhere beyond that tonight. That's for another topic. And so, sorry? That's the idea. Oh, and there's another thing. Just briefly, GANs, Generative Adversarial Networks, were originally designed to generate synthetic data when you didn't have enough. And people being clever came up with this other purpose. So you can think of it as a producer-consumer, but more like there's the good guys and the bad guys. The bad guys generate counterfeit money. The good guys to detect it. Makes sense. Now, there's something called cooperative adversarial networks, where the good guys go, oh, you know what, since you can't produce any more fake data, counterfeit money, that we can figure all of it out, here's some techniques you can use to generate better counterfeit data. So they produce more counterfeit data, so the good guys then have more stuff to test on to make their stuff better. There's something distinctly Machiavellian about this thing that I really, really like, but it actually exists. It's cooperative adversarial networks. You can check it out online. Okay, if you want, you can create your own GANs. It's on GitHub, and there's others that have done it as well. And just speeding up a little bit. What time is the session over? Does anybody know? 1:45? 20 minutes. Okay. Strap on your seatbelts. So, has anyone used Keras? Okay, 3 people. For the rest of you, you don't know what it is, so you don't know how much you can learn in 30 seconds. Let's find out. Notice at the top we've got a model. We talked about a model. It's called sequential. The naming is sort of irrelevant. And then the layers, import, dense, everything's connected. Dropout, we talked about that. Activation. Then layer conv2D, the convolution. Max pooling. And then down below, the shape is 3 channels. It's RGB, 32 by 32. Number of classes, 10. This is for MNIST, for example, the 10 digits. The model we instantiate is a sequential model. It's like a container. And then what do? We add a convolution, padding so that it pads out, and input shape is up there. Then we do add activation ReLU. Then another convolution, 32 3x3 filters. Then we add another ReLU. Then we do another max pooling, see the 2x2, maybe 3x3 if you want. And then we add a dropout. There you have it. You know what's in that model, you know why it's there, and you understand the purpose. We didn't train anything, of course, but that's what Keras gives you. Now,
where did you set exactly the convolution layers, the matrices?
they are generated for you by the framework, which is good. Otherwise, you don't want to go down that rabbit hole.
It needs all possible filters, right?
It will generate, here will give you 32 filters that are 3x3 with numbers that it uses, that are calculated using an internal algorithm. That's the key. And so now let's do the switch to TensorFlow. It was released open source November 2015. It's written in C++. It's got APIs for different languages. And I think it's an Apache license. And it's essentially a deferred graph execution. So there's two parts. One is defining a bunch of stuff, variables, whatever. And then there's the execution part. It takes place inside of a session. And the session is an instance of tf.session. And so you have a variable like ses. They don't even spell it out. Then you do ses.run, and you put your TensorFlow stuff in there. I know it seems kind of convoluted, maybe a bit pedantic. That's all in TensorFlow 1.x. TensorFlow 2, which will be next year, will use eager execution, which will look a lot more like Python code. I'll show you an example. At that point in time, maybe June or so, roughly, let's say, next year, 1.x will all be deprecated. It'll all be legacy code. But it will be supported for at least a year. And I think from what I read, Google itself has over 6,000 repositories with TensorFlow code in it. So that stuff ain't going anywhere. They're not going to drop it. But if you want to decide right now whether to wait for 2 to learn that versus learning 1.x, 1.12 just came out today, I think it was, today or yesterday. That's a decision you'd have to make. If you're starting fresh, either way, depends on what you need to do. If you've got a bunch of code, well, you can't convert it yet because there's hardly any eager execution-based code available. And they'll have tools to do the conversion. And if there's not a one-to-one, there'll be some code samples available and show you how to do that. So it's in their interest to help people with the migration to TensorFlow 2. So it's got all this nice support. Here's how you install it. And there's something called Google Collaboratory. Has anyone heard of that? Has anyone worked with Jupyter? Google Collaboratory is this Jupyter-based environment. All of it's online. And here's the nice part for those of you. How many people have a GPU on their laptop? No problem, because you get 12 hours of GPU time for free every single day with Google Collaboratory. It levels the playing field now. All the other stuff they're doing, that's what I use in my course now. It wasn't available last year, or I think it came out about 6 months ago. I don't remember exactly when. So just something to keep in mind. And so the use cases, again, pretty much, everything. I'll let you read about them later on. So as far as this, I mentioned in the graph, you've got the execution, then there's the first part. There's 3 things to keep in mind. There's constants, which you know. There's variables, which you know. And then there's placeholders. Think buffers. So constants, you assign a value, immutable. Variables are the things that are tweaked, that are being updated. The things that you want to. So y equals mx plus b, what are the things that you're tweaking? M and b. So those are going to be variables. Those are the things that you can save in a graph when you execute the code, and then launch TensorBoard, pointing to the directory where that file is, so that it will be rendered in a browser, and you can look at the accuracy, the error, all these graphs of all kinds of stuff. And it recite, it's really, really nice. Anyone use PyTorch? It's based on Python, and it's becoming popular among some. It's still small, growing, and for their data visualization, they use TensorBoard. So that's really, really nice. Now, I'm not sure if that will work. I haven't tried it yet with Collaboratory, what functionality is, but minor detail for now. So the edges are these tensors. Tensors are like multi-dimensional NumPy arrays, plus. There's other stuff going on under the covers, but data, they need to transform it. You have to do different sorts of things. These methods are built into it. And it uses, you'll see a lot of code that's out there using a combination of NumPy and TensorFlow. And over time, the layers of abstraction that are created in TensorFlow generally will incorporate functionality that exists in Python as a TensorFlow layer of abstraction. And so that way you don't have to do the context switching between Python, NumPy, and versus TensorFlow. That's one reason. And to simplify it, so you have less work. Because it doesn't look like obviously like Keras that we saw, it's not going to look like that, even with eager execution. But it's sort of getting there a little bit. And so I mentioned this already. The different size, 0 order, first, second, third, depending on the dimensionality of the array that you're working with. And we talked about that. I'm going to skip over some. Oh, here's an example. This is the sort of the general technique where you, the idiom is import TensorFlow as TF. Notice how we define the constant, tf.constant. If you print that in Python, it just gives you the metadata. Here's where the session comes in. Print that guy, you can do that, and it gives you the output. Then you close it. If you do it this way, you save that line, you do the width, and then it'll print it. And if you want to do arithmetic operations, that's how and the results are as you would expect. So the words are spelled out. And the older versions of TensorFlow, it'll have MUL instead of multiply. So they were changed a little bit, but basically the same. And StackFlow is your friend. Whenever you run into a problem, you can bet a lot of other people have as well. So just do an online search. If you copy paste some code and it doesn't work because it's an older version, you'll find the answer. And so now, remember I mentioned the placeholder is like a buffer. So for example, A and B are placeholders. Any C programmers here? Okay, so it's like kind of like a void pointer. And then you populate it with something when you need to. And in this case, we use feed_dict, feed dictionary, to specify values for A and B. And notice here, with TF session, I said, notice what we do, run C, comma, feed dictionary. So it gets the values for A and B, populates that, then initializes, and then computes C. That's generally how it works. And what happens is, you see the A and B, instead of A and B, you might have a placeholder for, you remember the data at the beginning I said back and forth every single time? Well, you may not update those edge weights every time. You might do it in mini batches, generally a power of 2, but it could be 50 or 100. So after every 50, then you do the update. So in the placeholder, you populate with 50 rows of data, do the processing, and then you get the next batch. So that's one place where it's used. And it's flexible in that you just say it's a placeholder, and then when you need to populate it, that's when you populate it with stuff. And it just works. And so here's some more different variations of how you can define something. Now, as you notice, Y2, what does that represent? What does that look like? Add, multiply W, X, B. The result is W times X plus B, which is linear regression. It can be whatever you want. It can be trigonometric functions, quadratic, cubic, whatever it is that you want, you can do it inside of TensorFlow with that. So, and if you go back, I'll skip over, the numbers aren't that important right here. One thing I didn't do was run this example so you could see it, but the point of this is, notice there we have an init. Init is necessary whenever you have variables, just the way it works with 1.x. And then you initialize it with a run init. And you don't have to populate everything. You could have 100 variables, maybe you only want to populate 5. And you could list them. This will do all of them. Notice the writer there is the file writer. That's the directory I selected. Under the current directory, tf_logs, it creates it if it's not there. And then what happens is it will save the output, which will be the variables. Placeholders are temporary contents of data. Those aren't going to be saved. And then at the bottom, you see a TensorBoard? That's 2 dashes. You can't tell by looking at it. And just specify the log directory. Then you go to localhost : 6006, which is Goog upside down, just in case you were wondering. And then you can see the graph. And then you can expand and do all sorts of stuff. So that's how you do it. And you can save tons of stuff in your code. And so eager execution, I'll just skip, there it is. X is 2, matmul XX, result 4. So that's eager execution. Problem is, there's only a handful of examples available. So you can try it. Maybe you'll figure it out and create a blog post for everybody. And then TensorFlow.js. We have just enough time, I think. Keep in mind one thing. Everything that you see, machine learning, deep learning stuff in a browser, underneath, there's a layer that handles, that does the heavy lifting. Anyone know what it is? Not quite that far, but eventually yes. But before, there's another layer, WebGL. So they've done the thankless job of providing it all for us. They don't get the recognition, but they really do deserve the credit for making this possible in a browser. And this TensorFlow.js was called deeplearning.js. It was another team at Google. They rebranded it, added more stuff. I don't know the details exactly, but it's more close akin to TensorFlow itself. And so it's kind of like Keras, but it's JavaScript. And so there's some layers in there. I want to get to the example here. It uses, it returns promises. Does anyone work with JavaScript? Okay, so you're familiar with promises. So you use async and await, and then you do your stuff, and then you invoke the code. This is a trivial example. It doesn't really do anything, just showing you how to use async. And then with this, I want to get to, this is sort of an example of something where you would use async and await, a little bit more, less trivial, I guess. And it's, there's an example here. This is what I would recommend that you do. Go to that download or code, the code, do the steps 3, A, B, and C, and I'll show you what happens. What you will get, not that, that's for CNN stuff. Okay, this is the code for that example. Can you see the bottom line? That JavaScript file that's generated? That's all that's there. And then the top link to the style sheet. And what happens is this code, all the JavaScript code is generated. It's about 35,000 lines of quasi-minified JavaScript. You're not going to learn how to work with neural networks with that code. So you're sort of, if you really want to learn about them, I would recommend going through Python. That's the biggest, most popular set of APIs that are available, and it's reasonable to work through. Okay, so what does this do? I will just relaunch it. I don't know if you can see this at the top. It says loading data. So it's actually training, going through that training process. The CNN that we saw before, that's what it's doing. And, oh, wait. Yeah, that's one. To do deep learning in your browser. Not everyone wants to use Python or Scala or Java from the command line. Some people want to live in the browser completely.
So you program with JavaScript and you have the neural network in the browser.
Yes. Sorry, did you see that brief? I forgot to connect. What's that? Okay, what's the password? What? Say again? Safe payment, okay. You mean that? S? Okay. All right. Good to know. And let's try this. We've got a few more minutes. There we go. See, it's training. It's doing batches of data. And again, you're not going to see that in the JavaScript code. So there it is. You see the ones that are red? Those are the ones where it failed. And the percentage, if you can't see it, 92. They got 46 out of 50. It's all in the browser. Pardon? Why did it fail? Well, because it's imperfect. It's an approximation, right? And I'm going to skip the other part. I just want to go back to a couple more slides. Where the heck is it? And the dpart.io stuff you can go check out on your own. And just, there's more stuff. We're basically almost out of time. just some books I've written, and I'm working on a TensorFlow book and another Python for TensorFlow as well, a short book. But if you know of technical reviewers available, we're looking for them. And I'm an instructor over at UCSC with a class in deep learning TensorFlow. Started 2 weeks ago, a bit too late to register. It's 10 weeks, 30 hours. I'll be doing it again in February, and a machine learning course in January. And now for the 2 books. Let's, by show of hands, what is the acronym ReLU? What is that? She raised it first. Correct. That was exactly the reason I asked for raising hands. Yeah. The other one, what's the name of the neural network that uses tanh? And sigmoid. Yes, sir. No. More specific. Did I mention that? Maybe, I'm sorry. It's LSTM. Did I mention that? I did mention that. Sorry, I gave it away. Let's try another one. What's the thing that you use to make sure that you can't collapse the neural network into one layer? Which? You got it. So, data cleaning or regular expressions, which one do you want? You take that one, you get that one. That's it. That's all I had to say. Hope this is worth your while. Enjoy the rest of your time.